everybody. Welcome back to Chem 140. It is time to finish up Unit 7. We're going to get started on Unit 8 today. We'll finish Unit 8 tomorrow. Do note that because this is an exam week, there is a slight schedule change. This class, it's not super different. Our lectures are on the same day, Monday and Tuesday. But on Wednesday this week, from 5 to 7, will be a review session. And I'm going to remind you of this tomorrow, and there will be probably an announcement on Tuesday night, like, hey, there's a review session. Please come to the review session. I'm going to bring a cat, because she always is here, although she isn't here this moment. I said I'm going to bring a cat. Nothing. We'll see if that actually got her attention. And you guys will hopefully bring questions for me that you might have for the first 8 units, because your exam is units 1 through 8. And we're almost there, so we might even have time on Tuesday to answer any questions that you might have. Other than that, you have other stuff that is due this week. So you got quiz 3. That's due today. Make sure you get that in by the deadline. That is a soft deadline, so you have tomorrow if you need it. Lab number 2 is due tomorrow. I think it said 5 May on there. I just realized that Tuesday is not the 5th, it's the 4th. So now it says the correct number. Also get that in by the deadline. You really don't want this shit to pile up because the exam is coming. And you want to spend time studying for the exam, presumably. There will also be another quiz for Units 7 and 8. That'll be quiz number 4. So that you can have that available to study from if you choose to. That quiz is just going to have the answers open. So once you've taken the quiz, it will show you your result, and you can look at all your answers and see how you did. And more importantly, see what was wrong so you could study it. Because those questions are going to show up in different capacities or similar questions or whatever on exam number 1. So I don't want you to go in blind on that and have no idea and then make the same mistake twice on the quiz and then the exam. But that does require you to take quiz number 4 before the exam. And it won't be due until the week after. So that is entirely up to you. That will be posted once we finish Unit 8, which will be tomorrow. So, all right, let's get to it. So we were here. I think this was the last slide we talked about. We talked about isotopic notation. I actually went and watched the video. What else did we talk about? We talked about carbonated water or something at the very end of the last video. But yeah, we'll get back on track here. So we've talked about isotopes. Isotopes are same Z, different A. So if I were to write the symbol of something like, say, I don't know, whatever this is. What is 8? 8 is oxygen, right? So these would be isotopes. They have the same Z, but they have different A. You can do the opposite process, and you'll get something that has the same A but different Z. These are called isobars. And what's interesting about isobars is that they weigh the same thing. Or at least they're very, very close to each other. To several sig figs, they are extremely close in weight. They have different chemical properties, so we could do chemistry to distinguish them. Nitrogen does different reactions than oxygen, for example. But if I tried to use a mass spec to separate these, it wouldn't work. So we need to isolate things based on either their chemical properties or their physical properties, wherever we can spot the difference. So here we can spot the difference in their chemistry. With isotopes, we can spot the difference in their weight or physics. So it's just handy to know. I personally have never really had to worry about isobars, but they're in the text, so we'll just talk about them real briefly. So in these pairs below, we can determine whether the 2 atoms that are represented by the symbols X and Y are either isotopes, isobars, or they're just unique. And so in this first example, well, I have different Z and the same A, so these would be isobars. These would be 2 different atoms that have the same isotopic weight. Down here I have the same Z, but I have different A, so these are isotopes. These are actually the same atom, or same element, with different numbers of neutrons. And then down here, these are just unique, because nothing matches. That's isobars. That's really all I care about for isobars. So as long as you know what an isobar is, you're in good shape. All right, so here I have a bunch of examples. This is just a little bit of a review from last time. So I'm going to give you these 3, we'll call them scenarios or whatever. I want you to write the isotopic notation symbol for each atom shown in the scenario. And then determine the relationship between the two atoms as described. Are they isotopes, isobars, or unique? I'll give you like 5 minutes to do that. Just scribble it down on your paper. We'll go over the answers shortly. 1 or 2 more minutes. We'll go over the answers. All right, let's go over the solution here. So for this first one, if I have an atom with 3 protons, that's going to be lithium. And it has 5 neutrons, so its mass number would be protons plus neutrons, so that's 8, because these two add together. The next not bromine. That was supposed to be an E, and an R came out. So the next one has 4 protons, that's beryllium, and 4 neutrons, so its mass number would be 4 plus 4 is 8. So these would be iso bars, because they have the same mass. All right, for the next one, a carbon atom, so that's this, with 7 neutrons, 6 plus 7 would be 13. And then a nitrogen atom with 7 neutrons, so that's 7 plus 7 is 14. These are unique. And then sodium 23, so that's 23. Sodium is 11, so we'll do that. And then sodium 24, these are isotopes. There you go. Those are the distinctions that you got to know. Isobar, isotope, and unique. Obviously, most combinations will be unique. But we can cherry pick a few that are isotopes or isobars. All right, the next thing that we need to do is we need to talk about why we care about isotopes. Which ones are common, which ones are not. And it turns out that it's very difficult to predict which isotopes are abundant. The best way to do this is to just investigate yourself. So go scoop up a sample of carbon. So like, say, get a briquette of charcoal, grind it up into a powder, and then put it in the mass spectrometer. And it will tell you the mass of all the atoms that pass through it. Many of those are going to end up being carbon-12. A small amount will be carbon-13, and then a very teeny tiny amount will be 14, and there's virtually none of this. I don't think that you'll find any carbon-15. So on the screen, I looked up half-life data for these, how long these isotopes live. And so when you combine a certain number of protons and neutrons in the nucleus, remember that protons will repel each other. Neutrons will stick to other protons. They don't really stick to other neutrons, though. So if you get too many neutrons, then the neutrons just kind of decay away. If you have too few neutrons, the protons repel and your atom falls apart. So there is a sweet spot. there is a Goldilocks just right sort of area. And that's where you have roughly like 1 to 1.2 or so times as many neutrons. And you can see this on the periodic table if you go looking up isotopes. All of the heavier atoms have way more neutrons than they have protons. They're not even close to being equal. But if you go too high or too low, your atom falls apart for different reasons. On the screen here, you can see the approximate half-lives that I've shown. So carbon-12 and carbon-13 are very stable. Their half-lives are well beyond the duration of any amount of time we can measure right now. So that's 10 to the 10 years or so is what I would quote that at, or more. Carbon-14 is not as stable. It has a half-life of about 5,700 years. So what that means is that if I had a gram of carbon-14, only carbon-14 was in there, I put it in a jar, and I came back in the year 8,721. That jar would only have half a gram of carbon-14. The remainder would have decayed into something else. Like, the mass would still be there. There would still be 1 gram of total stuff, but the other half of that would be, if it's carbon-14, it's probably going to turn into nitrogen-14 or something like that. Now, what things turn into is nuclear chemistry. Unfortunately, we don't really cover nuclear chem in this class. Nuclear chem is super cool. It's also surprisingly easy. But you take a class on it. I took a class on it as a fourth-year student. And I thought it was really easy. We got to actually go in a nuclear reactor because UC Irvine has its own nuclear reactor. And I got to see the swimming pool that has the... It's not really a swimming pool. It's just a giant pool where the reactor is in there. It does glow blue. You do have to wear a radiation badge when you walk in there. I did not receive a appreciable dose being in that room, which is probably good. But yeah, things are radioactive. Carbon-15 is so radioactive that you can have a gram of it and it lasts 2.5 seconds before half of it decays. And then after 2.5 more seconds, the other half of it will cut down by a factor of 50%. And eventually you just won't have any. So getting a charcoal briquette in our example from earlier, the odds of you having any atoms of carbon-15 on there are approximately 0. Because it just doesn't last long enough for you to get it to the detector. If it was in there at some point when the charcoal was fused together, which would have been a very, 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 very long time ago. So by doing the experiment, we can calculate all these numbers and see what isotopes exist and what isotopes are abundant, and so on. We're going to talk about half-life again a little bit more in 163 when we talk about reaction rates and decay and stuff like that. But we can use this... Do I talk about stable isotopes? I don't. I'm just checking ahead here. Yeah, we don't. Okay. So what we're going to do here, I'll just write it on this page right here. These isotopes, which last long enough for us to detect them, we're going to call these naturally occurring. Carbon-14 is kind of the edge case. Like, 5,000 years is not a lot of time. However, if something lived 5 to 10 to 15,000 years ago, like, say, a tree or something, it would have carbon-14 in it. When the tree dies, it stops accumulating carbon-14 because it's no longer absorbing nutrients from the soil. And the amount that's in it would decay over time, and we could calculate it. That's how carbon-14 dating works. Other isotopes that are just too reactive that we can't find, we're going to call these synthetic. Because in order to observe them, we have to make them. And that's where particle colliders come in. You could fire like protons at a boron nucleus and get a carbon nucleus if the protons stick for a little while. Or you fire neutrons at something and increase its mass, or do whatever. You could do all sorts of things and then observe the results. That's basically what CERN is doing, or the Large Hadron Collider and stuff like that. For our purposes, we really only care about the naturally occurring ones. These are the ones you're going to find when you go outside and go scoop in like the carbon bin, or get a bunch of oxygen from the atmosphere, or nitrogen, or whatever that you're examining, or mine up uranium, and so on. When you do the analysis on the mass spec, and again, we'll talk about mass spec in Chem 161 in more detail, you're going to get this known as a percent abundance. The percent abundance just basically tells you, okay, this percent is this isotope, this percent is this other isotope, etc. Now, these percentages are for random samples. Because there are just so many atoms in a given sample, the odds of you getting a random sample are quite good, assuming everything is well mixed. And for the most part, it is. If you dig it out of the ground, odds are it's probably going to be well mixed because it was well mixed when the Earth was a fiery ball of lava and still cooling and forming, right? So all of those things that have hardened and then congealed and then we eventually mined up billions of years later, probably well mixed. But there is some variation depending on where you mine up your samples for, and sometimes that's reported. That variation goes down to several significant figures, so you might see a range when given percent abundance on tables like, say, Wikipedia. But for our purposes, I'm just going to tell you the percentages, and we'll just assume that that's fact. Because for whatever sample I got this from, it was true, and we'll just assume that's representative. So, for instance, in a sample of carbon, 98.89% of that carbon is carbon-12. The remainder is other isotopes. Almost the entirety of that is carbon-13. There is extremely small amounts of trace carbon-14. The amount that you will find is generally proportional to the half-life. So things that are extremely stable, there's lots of. Things that are relatively unstable, there's almost none of. And again, the reason for that is, well, if they decay really quickly, they were formed whenever those atoms were formed, such as in the core of the sun, not the sun, of a star, I guess I should call it, be more general here. Such as the core of a star, then the star exploded, and all that material went everywhere else and then coalesced into planets. During that interval of time, those isotopes would have decayed away, so we would never have found them. But the ones that are much more stable will stick around. And again, half-life is unique to each isotope. It has to do with the number of protons and neutrons, which is very difficult to really predict at our level. I certainly don't know how to predict it. I could guess, like, oh, maybe this is stable, but I could not tell you to any degree of certainty where the half-life would be. Like, would it be seconds? Would it be days? Would it be years? There's no way I would know that without just looking it up. Now, we're going to be dealing with very small masses, and writing numbers like this is cumbersome. So if I wanted the mass of a carbon-12 atom, I don't want to be writing 2 times 10 to the 23, or 2 times 10 to the minus 23 grams every time, and then only have 1 sig fig for that. So what we're going to do is we're going to assign this a different unit. We're going to throw the pen on the floor. That's what we're going to do. Where did it go? Wow, how did it go way over there? I must have rolled off of my desk or something. I thought I dropped it on my lap, but then it landed like on like the bottom shelf of my desk for some reason. Oops, and then this disappeared. Oh, no, I advanced the slide. That's what I did. Okay. So we're going to assign this value to a specific mass. So we're going to say that this is 12 AMU. This is actually just a definition. Carbon-12 weighs exactly 12 AMU. And I think I show that on the next slide. I don't know. But from that definition, what we can then do is we can pick apart all the pieces that are in carbon-12, which would be protons and neutrons. And all the electrons too. Electrons do have mass. And we can assign a mass to each of the parts. And you'll notice that's 3 sig figs. Or 2, actually, because this is going to round. We get some approximations here. So a proton is roughly 1 atomic mass unit. A neutron is also 1 atomic mass unit. And an electron is so tiny that it's some fraction of a mass unit. We're going to just call it 0. Now, these numbers are determined experimentally To a rough approximation, this is okay to just make an estimate. So for instance, if I look at iron 56, what number is this? 26? Yeah. Oops. If I looked at this, I could say, okay, this probably weighs about 56 AMU. And that's good enough for an estimate. And we can use that information to look at the periodic table to look at mass numbers. And so let's grab P table and do that real quick and have a little bit of a discussion here. So P table, I type in PT and P table comes up. So window capture, P table. There we go. So I'm just going to click on an element here. Here's iron. And you can see that down here at the bottom, this number right here, this is the mass, the atomic mass of iron. But that number is the average of all the isotopes that are naturally occurring. So on average, if you scooped out a bin from a bin of pure iron, the average atom of iron in there would weigh 55.845 AMU. Now, by looking at that, you could say, okay, well, I'm going to round that to the nearest integer. That's 56. So the most common isotope of iron is probably iron 56. And this is pretty reliable. So the most common isotope of chromium is probably chromium 52. The most common isotope of fluorine would be fluorine 19. And so on and so forth. And you can do this for all the elements on the periodic table, with some exceptions, because in some cases you get a weird number. So like magnesium over here, it's kind of in the middle, right? Probably closest to magnesium 24, but it's ambiguous. What if there's a lot of magnesium 25, but also a lot of magnesium 23 or something, and the average gets tugged around? In fact, this actually does happen for some elements, such as bromine. Bromine, you might think, oh, well, bromine 80, most common. Nope, turns out all bromine is 50-50, 79 and 81. There's 50% bromine 79 and 50% bromine 81. That's nature's way of going, haha, sucker. And there's no way to know that. But you can make predictions about what is probably the most abundant natural isotope by looking at the periodic table and just rounding to the nearest integer. And that will usually work. Just turns out for bromine, it totally doesn't. Now, what if we want to go into more detail than that? Well, then that's where all of these extra numbers come in. And so we would report these extra decimal points for things that we weigh so that we can calculate percent abundance or the average atomic mass or whatever. And so this is where the numbers on the periodic table that I was highlighting before, we'll put this back here. So where it says bromine over here, 79.904, how do we calculate that number? Where does that come from? That's what we're going to do today. We're going to learn how to do that. All right. Now, we have defined that carbon 12 is exactly 12 AMU. We just said that that's true. Based on that, we can then weigh any other atom and use 12 as a reference, because with our device, if I weigh something and I set a mark where 12 is, and then I weigh something and I am some ratio towards or past that mark. For instance, on the screen here, I have boron 10. Boron 10 is 0.83442 times the mass of carbon 12. So I do the math, and this is the result that I get. Boron 10 is 10.013 AMU. It's close to 10 AMU, but those extra numbers that were here on the table here throw it off just a little bit. They make it a little bit too large if my atoms are small. And they make it a little bit too small if my atoms are bigger than carbon 12. So this is where isotopic masses come from. So what this is an isotopic mass. Because it's the mass of an individual isotope. If you know all the isotopic masses of the isotopes that naturally occur, you can then find the atomic mass by taking the weighted average. Now, how do weighted averages work? Well, let's talk about how averages work. So if I have these isotopes, and I want to find their average, well, that's very easy, right? 12 plus 13 plus 14 divided by 3 is 13. Wow, you did that so fast. Yeah, because this is one less than 13. This is one more than 13. So this is how you do a normal average, right? Now, we can rewrite this formula like this. That's the same thing, right? And then I can distribute this 1/3 into each thing, and I would get something that looks like this. And these would all still equal 13, right? These things right here, these fractions that are in the front, these are our weights. And so what this is saying is that, well, the average mass of all of our atoms would be 13 if and only if our sample was 1/3 carbon-12, 1/3 carbon-13, and 1/3 carbon-14. But that's not true. We don't have a third carbon-12. We have like 99% carbon-12, 1% carbon-13, and essentially nothing of carbon-14. So this term right here shouldn't contribute anything because there's not any of it. And this term right here should contribute a very tiny amount because there's a very small amount of it. So if I change the weights, this number changes. And what it changes to is this, which is the atomic mass. And we can show that by just doing the calculation. Punch in 0.99 times 12 plus 0.01 times 13. And you should get 12.01, which is what's written on the periodic table, right, for carbon. Now, obviously, I only did 2 sig figs. If you wanted more sig figs, you would have to write out more numbers for your percentage. And in fact, I'm playing fast and loose with sig figs because 12 times 0.99 is probably 12, and 13 times 0.01 is probably 0, and you'd get 12 as your answer. But you see the idea here. So we need to take the weighted average of isotopes by inputting, instead of whatever fraction would be equally distributed for a normal average, put in the percent average, or the percent abundance, actually, in for that. So here's the formula for this. So I'm going to put my percent abundance of whatever the first isotope is times its mass, then the second percent abundance times its mass, and so on and so forth. And I'm going to do that until I've done that for all the isotopes. And then whatever that result is, I'll sum it all together. There's a different cat in here. Hi, different cat. Kresnik, are you going to say hi to my students? Say hi. Say hi, meow. 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 No, he doesn't want to talk. Kresnik will meow at me, but he won't meow in the mic. Huh, buddy? Alright, so we've seen this formula. What do we do with it? Let's apply it to try and get the atomic mass of something off the periodic table. So we'll do that here. Here's boron. We're going to calculate the atomic mass, and I've shown you boron right here. This is the number we should get when we do the calculation. I have run boron through a mass spec. Actually, what I did is I looked this up on Wikipedia. And I found that boron 10 is about 20% abundant, and it weighs this much, 10.0129 AMU. Boron 11 is the 80% most abundant, and it weighs 11.0093. So let's find the weighted average. So the atomic mass will be the mass of boron 10 times the percent of boron 10 plus the mass of boron 11 times the percent of boron 11. And so let's just enter all those numbers. I've been talking for 5 hours. No wonder my throat's parched. Get more water here. So the mass of boron 10 was 10.0129 AMU times the percent of boron 10. I'm going to express that as a decimal because that makes the math easier. Plus the mass of boron 11 times the percent of boron 11, which is that. And now we punch in our calculator, but we got to be mindful of sig figs. So the first operation we're doing here, this is a product. So I'm going to times those together. And my answer should have 3 sig figs. Because of this number right here, 0.199 only has 3 sig figs, so my answer will also only have 3. Then I'm going to do the next one, 11.0093 times 0.801. That result will also only have 3 sig figs. And then for this part, I'm going to add these numbers together, which I'm going to do vertically. And we're going to round to this position here. Oops. Clicked on an arrow there. And the result that I get is 10.81. So this is my result. And you can see that that's real darn close to the number on the periodic table. They got more sig figs than I did because they probably used percentages that were more precise. So if you had more digits here, you could keep more decimal places in the multiplication steps and then preserve more of them when you finish the answer. So there you go. That's how you calculate atomic weights on the periodic table. So the average scoop of boron will weigh 10.811 AMU, but of those atoms in there, only these weights exist. So nothing actually weighs 10.811. You just have a bunch of 10s and 11s, but there are more 11s than 10s, so on average they weigh 10.8. All right. Any questions, let me know. That's how we calculate atomic masses. Now, there is another type of problem that you can do. And that is, well, if I tell you what the weights are, can you tell me what the abundance is? We'll use this as an example because chlorine is a very common 2-isotope abundance sort of system. And we can go look up our answer to see how well this compares here. Now, how this works is we're going to write out the atomic weight equation. So I'm going to say the average atomic weight will be whatever the mass of chlorine 35 is times the abundance of chlorine 35. Now, I'm just going to write 35 here, and you'll see why in a second. Plus whatever the mass of 37 is times the abundance of 37. Now, let's check off what are the things that we know. So I know this number because it's this number right here. I know this number because it was given in the problem statement, and I know this number because it was also given. However, there is an issue. I have 2 percentages, and I have to solve for both of them. And as written, that's not possible. You cannot solve one equation with 2 unknowns and get the solution. In fact, there are infinitely many solutions. But we know that doesn't make sense, right? There should only be one situation for this. So we need another equation in order to solve this system of 2 equations here. So I need a second equation in order to do this. What could that second equation be? think about what you know about this problem and see if you can type in the chat what the second equation is, and I'll tell you if you're right. Any idea at all? I'll give you a hint. It has to do with the percentages that we underline. We're going to make another equation that has those in them. What relationship do those two percentages have with each other? Because if it's true, you can make an equation out of it, right? What could the relationship be? Well, if I relate... There you go. So yeah, you're on the right track. So if you know one of the percentages, the other one must be the other part of it to get to 100, right? Or I could just write this. Whatever percentage 35 is, and whatever percentage 37 is, and I add those together, I should get 100%. As a decimal, that's just 1, right? So now I have two equations and two unknowns. I can now solve the system of equations. Guess what we're going to do? We're going to do absolutely nothing, apparently. There we go. We're going to solve the system of equations. I'm going to make this real small just because I'm going to rewrite the system of equations right here. This is going to take a second, so here we go. Oops. All right, so we have a system of two equations and two unknowns. I'm going to do this. Whatever the percentage of 35 is, we're going to call that x. And whatever the percentage of 37 is, we're going to call that y. So this becomes this, this becomes this becomes that, and this becomes that. And now you could totally solve this equation because you've done this in Algebra 2. Remember way back in high school when you had to solve systems of equations? Yeah, we still actually do that. We don't teach you that because it's an exercise. We teach it to you because it's useful. And here's where it's useful. Now, unfortunately, that does require us to do a bunch of algebra. So here's what we're going to do. I'm going to substitute this equation into this equation. So I'm going to rewrite equation 2. And I'm going to do this. We're going to solve for x. That means that x equals 1 minus y. Since I know what x equals, I can then substitute into equation 1. And when I do that, that looks like this. Here's what x was. We'll replace it with 1 minus y. Y stays the same. Now I have one equation with one unknown. We can now solve for y. So let's do that. First, I'm going to do the algebra, which means distributing this. So m average still equals that. m35 times 1 is just 1, minus m35 times y. And then I have this term over there too. I don't really need these parentheses anymore, so we'll get rid of them. Now what I'm going to do is I'm going to move everything over to the left side that does not have a y term in it. So that's just this. So this is going to go over there. And that's going to leave negative m35 times y plus positive m37 times y. I'm just going to switch these two places so I don't have this negative floating around in the front here. Now I have two terms with y's in them. How do I solve for y? Well, I can factor out y, right? That's the same as me writing this. That was supposed to be a 3. Right? I could do that. That still equals this. And then finally, I can solve for y by dividing by this part, right? So there you go. That's what y will be. And remember that y is equal to the percentage of isotope chlorine-37. So now I can take all these numbers that are in this problem here and the atomic weight of chlorine here, and we can solve the problem. So let's do that. So now we have the average mass, which according to the periodic table is 35.453 AMU, minus whatever chlorine-35 was, which was 34.9689 AMU, divided by the mass of chlorine-37, minus 35 again. And so now what we have to do is we have to do two subtraction problems and then divide the results and pay attention to sig figs. So be careful when you do these types of problems because the sig figs matter, right? If I do 35.453 minus 34.9689, if I were to do these vertically, I would end up rounding whatever result I get to the thousands place because that's the first position that there's a sig fig for both my numbers, right? So I'm going to hit enter on my calculator, and the number that it spits out is 0.4841, which I will report to the thousands place. On the bottom, I get to go to the 10,000ths place because both of those numbers have that. Oops, I didn't mean to do that. Well, now it's bigger now. That's actually no good because I need, hold on. I need that. So I'm going to punch this in my calculator. 36.9659 minus 34.9689. And I get to keep to the 10,000ths place. So that number is 1.9970. The AMU cancels out. And now I have a 3-digit number divided by a 5-digit number, which gives me a 3-digit number, and that number is this. So by doing all this algebra, we have calculated that, what did we solve for? We solved for y. So y equals 0.242, or 24.2% abundant. And then we could do the same thing for x, but that would be dumb when we have this equation right here. So x must just be 1 minus this number, or 0.758. There you go. That's how you do the algebra. And that is a pain in the ass. There must be a better way, right? Sorry, hold on. This requires some setup here. There must be a better way, right? This is Wolfram Alpha. I don't know if I've shown you Wolfram Alpha yet, but I'm going to show you Wolfram Alpha. All right. Now, oops, what did I just do? I accidentally turned it off, didn't I? I must have hit the spacebar or something. Okay. In Wolfram Alpha, we can type in our equation. And so what I'm going to do is I'm going to type in the equation that we had before. Now, obviously you can't see it because it's not on the screen anymore. But so we're going to do M average equals M35 times X plus M37 times Y. We're going to leave the Y's in there, but I'm going to fill in all the rest of the numbers. So M average was 35.453 equals, and then I want the isotopic mass of, let's just get rid of all this for now, of chlorine 35, so that was 34.9689 times X plus the isotopic mass of chlorine 37, which we'll call Y. There's one equation. I'll hit a semicolon. X plus Y equals 1. Solve. And this is what it got, which it's very small on the screen, so let me capture that for you real quick. How does that compare to our answer? So here's our answer. Well, there was our answer until I scrolled it off the screen there. And that's not going to work. I'm going to have to go back to the previous page. So we got 0.758 and 0.242. There's what Wolfram Alpha got. So, you know, work smarter, not harder, right? So you can do all the algebra, and you probably should for some practice. I'm just resizing this window so I don't have to do it later. Yeah, there we go. Because on Canvas, I'm just going to tell you, report your answer to some number of sig figs, right? So instead of doing the algebra 70,000 times, use Wolfram Alpha. If you don't have a calculator handy, Wolfram Alpha is an excellent calculator. There are the percentages I got when I did this problem, which are a little bit different than what we just calculated. I might have made a math error here somewhere, but close enough for government work. All right, I showed you the example, so now what I want you to do is to do that for me. Although we are at the top of the hour, so we're going to take our break now before we do this. So when we come back, you can try these 2 problems here. So we'll get the title card back out. Let me get the Zelda Wave. Everybody likes Zelda Wave, so. And we'll see you in a bit. chilling listening to the music here. Zelda wave. Do 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 do. All right, we're back. Let me put these problems on the board here for you to try. The first one is just compare to the periodic table. You can use p-table for that. The second one is the percent of these mystery isotopes. Now, obviously, you can't compare this to p-table because X is not an element that exists, but there is an intended answer, and you can use Wolfram Alpha to solve the system of two equations. You just need to set up the system of two equations first. Okay? So, give that a shot. I've already linked Wolfram Alpha on there. I will link p-table again in just a second, but go ahead and get started, and we'll go over the answers in about 5 or 10 minutes. So the answer to the first one is obviously just on the periodic table, but type your second answer for element X. Type its percentages in the chat when you are done. Two more minutes. We'll go over the answers then. All right, so what we'll do is, oops, I got to get the canvas up here for Photoshop. That'll work. Wait, what the heck is this? What is this dot here? I don't know. There was like a dot on my screen. Some object. Is it this? Oh. Can I make this bigger? I can move it. That's... whatever. That's a problem for future me. Well, future me is in about 20 seconds here, so the average mass of silicon will be the first isotope times its abundance. So I'm just going to go straight to the numbers here. Times 0.92223 plus 28.9765 for the second isotope times its abundance 0. Oops, lost where I was on the screen here. 0.046858 plus silicon 30, which is 29.9738 AMU times its abundance 0.030921. All right, so this first one is they're all 5-digit numbers times each other. So the only issue we're going to run into is when we do addition. So I'm going to punch these in. 27.9769. Oh, actually, that's a 6-digit number. Well, the percentages are 5 digits. 0.92223. So this first one becomes 25.801. The second one becomes 1.3578. And this third one becomes 0.030921. 0.92682. These are all AMU. Okay. Now we just add all those together. This number will go to the thousands place, 10 thousandths, 100 thousandths. So this is going to be the place that we round to. When I punch all these into the calculator, of course, I got to punch them in correctly. Oops. 357, that's not 7, plus 0.92682. And so when I do all of this, I get 28.086. That's the result I get. What does silicon say on the periodic table? Mine says exactly that number, so that's pretty good. We did it correctly. For the unknown element here, I'm not going to solve out all the algebra because you've already seen me do that. What I'm instead going to do is I'm going to show the equations that we should create here. So we'll do M average. This will be the template here. So this will be, mass of the first isotope, which is 70, times percent 70, plus the mass of 73 times percent 73, which I'm going to rewrite. And so that will be, well, if the average mass is 71.255, that would equal the mass of 70, 69.938, times x, we'll make x this, plus the mass of 73, which is 73.014, times y, so y is this one, And then we know that x plus y equals 100%. So I'm going to put these equations into Wolfram Alpha. I do need to put that on my screen so I can see it here. Capture a window. Capture this. Go. Nothing has happened because my window is teeny tiny, so deleted. We'll add a new one. Window capture 3. Capture that up here. That didn't work. Oh, I see what I did. Okay, yeah, I gotta do. There we go. So that's the old equation. So let's make that bigger so we can all see what's going on. And we'll type it in there. So we'll just go 71.255 equals parentheses 69.938 times x plus 73.014 times y semicolon x plus y equals 1. And that's what it gives me. So it says that x is 0.57. That's not a 7. There we go. 7, 1. Y is 0.428. I'm doing 3 sig figs. If I did this the long way, I would get some number of sig figs. Whatever. I'll just put a second or fourth digit in there. So 8 and 2. I'm just looking at these and trying to figure out how many sig figs I would have. It's probably going to be 4. Yeah, it looks like 4. Okay, there you go. So for that isotope that we looked at, X70 is 57.18% abundant, and X73 is 42.82% abundant. All right, there you go. That is it for Unit 7, which means Dancing Orc, or Thumbs Up Orc, I don't know. There he is. Oh, I clicked the thing. There we go. Hooray. Okay. I need a second to get Unit 8 out. Close. Okay, now it should appear. There it is. Okay. All right, let's do a little bit of Unit 8. Not that there's very much of Unit 8 to do anyway. There's only like 20 slides in this. Unit 8 is about the periodic table, so you're going to need p-table. Fortunately, I linked it to you right there, so you can just click on it. It's right there. It's right there. Just click on it. And we're going to talk about how the periodic table is constructed and some various trends and categories that are going to be relevant to us, particularly in 161. So let's get started. One of the first things I showed you early on in the quarter when we were talking about the scientific method and how we observe information to generate scientific facts, condense those into scientific laws and then theories, we showed that elements in the first column of the periodic table react in water. And I have it linked there, but it's just all the elements exploding again. We don't really need to see that again. Now, the elements being placed in those columns because they have similar reactions was not coincidence. We did this by design. It's also not coincidence that all the elements on the very far right of the periodic table in column 8 are, column 18, it's 8A, are unreactive. Why would these things be true? And it turns out, well, it's true if we put them there. And by we, I really mean this guy. This is Dmitry Mendeleev. Mendeleev was a very, very prominent chemist who discovered lots of different facets and facts about various elements and said, Well, instead of just having all of this information, what if we tried to condense it into a table? And so he did. And so what his periodic table did, and I can actually get you a picture of Mendelev's periodic table. So let's see here. Periodic table Mendeleev. Maybe it's Mendeleev. I don't know how to actually pronounce his name. There we go. So Mendeleev got a periodic table. We'll capture that on the screen. There we go. And it'll look like this. The one that you see on the right here. We'll make this bigger. We'll chop my little orc picture out of there. Now, you could see that Mendelev's periodic table was a little bit different than ours, but a lot of the things that we have on our periodic table still remain to this day from his findings. And so everything in blue was an element that Mendeleev knew existed. All the remaining elements in pink weren't known at the time, and some of these in here he discovered, actually. So, for instance, where you see gallium right there, where'd my cursor go? Is my cursor on the screen? It's not. There it is, right here. So here's gallium right here. Gallium was not known at the time when Mendeleev constructed the periodic table, but what he did was he said, okay, I expect this element to have some mass between 65.4 and 72.6, and it's going to be real similar to aluminum and indium, and yttrium and boron, anything in this column, really. And so his prediction was look for a substance with these properties. And it turned out that it was exactly right. He was able to identify the existence of gallium before it was ever discovered. And so the predictive power of the periodic table is super, super useful in an era when not all the elements have been discovered or isolated. Nowadays, it's just useful for other things, but we use the periodic table for all sorts of predictive properties, and so that's what we're going to do. We've arranged the periodic table in order of increasing number. This is actually an older slide, so you'll notice that down here, these elements are blanks. These have been filled in. All of these elements now have names because some organization has decided on what those names are. I thought there was another thing after that. And so we are going to explore the periodic table, assign some categories to the table, and then discover some trends that are obvious and maybe not obvious. So the first trend that we want to talk about is the group. It's not really a trend, actually. These are just categories. So a group is any column on the periodic table. So if I go back here, there are 18 groups going left to right. There's a region in the middle here, right here. There, I don't have my pen selected. There we go. Right here, this is not a group. This is actually just sort of a shortcut. Those elements should be squashed into that gap, but there are too many of them to fit on a reasonable sized table. So the periodic table just kind of looks like this. But all the other groups are numbered left to right, 1 through 18. So 1, 2, 3, 4, 5, da 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 da. 18. There is another numbering system that goes 1 through 8A, and so these two columns over here are considered the A columns, and the remainder over here are A, and then this in the middle is B. That's an old nomenclature system. I will refer to it, but we're going to try and stick to the 1 through 18 just because it's easier to deal with, since all modern periodic tables are just numbered 1 through 18. So we're going to assign every column a group number. With the exception of those two rows at the very bottom, they don't have a group number because they're kind of an exception. Groups run up and down. Any element that is within a group behaves similarly to other members of its group, though the speed at which the reaction goes can be different. We're going to discuss why that is more in Chem 161. We talk about like ionization energy and quantum mechanics and electron configurations and things like that. Going across the table, left to right, are rows. We're going to call those rows periods because it's a periodic table. Every time you go to a new period, you establish the patterns all over again. That's why it's periodic. The period number is not super useful other than just telling you where an element is, but there are some things that we will refer to in 161 162, particularly what the valence shell of your electrons is. The period number tells you the highest level of valence for your electrons. So anything in period 5 will have 5 layers of electrons, for example, and the outermost ones will be in level 5. Again, more on that in 161, since that's kind of the whole point of that class. On the screen, I have a bunch of labels. These labels are worth knowing because we will refer to them by their name quite often. Just for clarification, this element right here, hydrogen, is actually in the non-metal group. I realize that it looks really close. These colors right here look really similar. They're actually different. But anyway, it's worth knowing what the groups are. So group 1 is called the alkali metals, and group 2 is called the alkali earth metals. It should actually say alkaline earth metals, but that's okay. These two groups are called that because if you drop these elements into water, you create an alkaline solution. An alkaline solution is basic. It has a pH greater than 7. These are words that exist, and you probably don't understand them just yet, but you may have heard of them elsewhere. We'll talk about that in 163 when we do acid-base chemistry. On the other side, we have, it says inert elements right here, but a better name for these would be noble gases, because that's the common term ascribed to them. Noble gases, like all nobility, sit on their asses and do nothing. These elements are unreactive. They just hang out. Halogens are common enough that they have their own category, and you should probably know which elements are the halogens because they are ubiquitous. So you might have heard of a halogen lamp, or you might have heard of halogenation reactions. Or maybe when you go swimming at like a swimming pool, nobody does that anymore. It's the pandemic, right? But public swimming pools need to be halogenated so that they maintain a specific pH so that any bacteria or whatever gets killed. That's what stings your eyes when you go swimming after they put that white powder in. Those are all halogens. Those are all examples. The others that are important are transition metals. It's good to know where the transition metals are. And then down here, there are many names for the rare earth elements. So we've got lanthanides, which are the top row. And we got actinides, which are the bottom row. Non-metals and other metals, like, you don't need to know which ones are the other metals. We're going to talk about metals versus non-metals in just a second anyway. Actually, maybe not in just a second. We'll do that on, well, how much time do we have? Oh, we have like 15 minutes. Okay, we might get to that. But yeah, use these categories for this next activity. Oh, we're going to talk about metals right now. When I ask you to describe stuff. All right. One property on the periodic table that we can easily see is metallic character. Metals tend to be on the very far left of the periodic table. Non-metals are on the far right. And there is a zigzaggy region that's sort of in the center of the right block where we have metalloids. And so we'll discuss these in a little bit more detail, but here's the picture of that. So I'm going to grab the felt tip pen and we're going to draw this staircase real solid so that you can see it. What I have drawn here, this is the metal, non-metal line. And things that touch the metal, non-metal line are metalloids, with one exception that we care about, and that's aluminum. This is polonium, this is astatine. These are radioactive. So we generally don't care about them. But for everything else that touches the line, everything that touches is a metalloid. Metalloids are sort of between metals and nonmetals, and I think I list the properties. Yeah, we're going to talk about what those properties are on the next page, but anything to the left is metallic. Note that these guys down here all go in this spot, so they're all on the left too. Anything on the right is a nonmetal. Now, of course, depending on the application, you may want a metal to do stuff. For example, you would not build a plane out of a non-metal. It would decompose very quickly, or crumble, or even catch on fire. Likewise, you would not want to build a computer out of a metal entirely because it would make it very difficult to have logic gates to control electron flow, because your electrons would just flow uncontrolled through your metal, and it would heat up and probably catch on fire. Generally, things catching on fire is bad. We would like to avoid that. So let's explore the properties of these substances in a little bit more detail so that you can get a general gist of why we'd want to use these. So the first thing that metals can do is conduct heat and electricity really well. If you're trying to conduct electricity, such as, say, through power lines, you don't want to make your power lines out of graphite. Graphite doesn't conduct electricity. But copper does. Copper conducts it really well, and copper's abundant. So all of our power lines and all of the wiring in your apartment or house, it's all made of copper. We make cookware out of things that are made of metal, not only because it doesn't melt or tarnish or whatever, but because cookware conducts heat very effectively. A cast iron skillet, for example, transmits heat very well and evenly throughout the pan, so you can cook on something that is roughly the same temperature, and you don't have just hot spots, for example. Metals are also malleable and ductile. What that means is something that's malleable, when you hit it with a hammer, instead of it shattering into pieces or breaking or fracturing, what tends to happen is it becomes thinner and then its surface area increases. So you can compress something that is malleable with enough force and make it thinner and thinner and thinner and thinner and thinner and larger and larger and larger and larger, increase its surface area. This is how aluminum foil is made. You just take a chunk of aluminum, you squash it into a sheet, and then you tug on the sheet until it is the desired thickness, and then you cut it. That's aluminum foil. Ductile is the same thing, but with wires. You pull on it in one dimension and you eventually get a wire. You keep pulling until you get the gauge that you desire. The last property of metals is that they're shiny. Just like Bender. That's why he's there. What does Bender always say? Bite my shiny metal ass? Yeah, that checks out. He's a metal. Non-metals have none of those properties that I just listed. So things like iodine or carbon, non-conductive. You heat them and they either burn or decompose without actually getting hot very effectively. If you hit them with like a mallet or try and draw them into a wire, they end up breaking or fracturing because they're molecular most of the time, although some other examples exist. And they're certainly not shiny or even pretty to look at. Things that are metalloid are somewhere in between. Silicon, for example, is a semiconductor. It does not conduct electricity as effectively as, say, iron or copper, but we don't want it to. And that's good. However, it is not as much of an insulator as, say, iodine or carbon or oxygen or anything like that. So, all right. In this periodic table, I have put the transition metals beside the lanthanides and actinides and sort of spaced out where all these elements fit in. This is probably what the best visualization of the periodic table should be, but it's really hard to make this a poster and put it on your wall because no poster or no wall is big enough for said poster. And then everything would have to be really tiny and it wouldn't be very good to hang on the wall in the classroom. So what we have done is we've taken these two rows down here and we have set them underneath the periodic table as their own two rows, lanthanides and actinides. There are other periodic tables out there. You may look up alternative periodic tables and find like the spiral one, which looks really cool, but again, hard to read. So there's not one universal idea for how we should arrange these elements, but there's one generally accepted idea, and that's the regular periodic table that you see on ptable.com. For these exercises, what I want you to do is find these elements on ptable, and then I want you to give some sort of category that describes the element. Also tell me the period and the group that you find the element in. And then finally, tell me if it's a metal, nonmetal, or metalloid. I'll give you a few minutes to do that, and we'll call it a day. There's not going to be much left for Tuesday's lecture, which will be Chapter 8, so we'll probably start Chapter 9 a little bit then. But yeah, so go ahead and do these. We'll go over the answers together shortly. One more minute, we'll go over the answers. All right, so let's go over the answers here. I'll kind of have to slide this off the top here. That'll work. All right, so the first one's fluorine. So fluorine is in, so it's group 17, period 2. And for a term that I would give it halogen. Name, period, group. Oh, and then also nonmetal. There you go. Then next we have, I gotta go back over to it, calcium. So calcium's over here. That's the wrong window. That's Photoshop. There we go. So calcium is in group 2, period 4. It is an alkaline earth metal, and it's also a metal. We got krypton. That's way over here. Krypton is in group 18, period also 4. It is a noble gas, and it is a nonmetal. Then we got gold. Gold is in group 11. It's in period, I gotta count all the way down, 6. It is a transition metal, which of course makes it a metal. And then of course I picked thorium, which I didn't get on the screen here, so I gotta scroll down. There it is, boop. So thorium is in group, doesn't really apply. There is no group for transition, or for lanthanides and actinides. But it is in period, and you can calculate that. Oh, it's right there. So that's period 7. It is an actinoid, and also metal. And you could have said, instead of actinoid, you could have just said inner transition metal or rare earth metal or whatever label was on there. We're not going to talk about lanthanides and actinoids very much at all, because they're sort of beyond the scope of this class, and there is interesting stuff that can be done with them. We need to talk more about other topics before we can get to that. Yep, that's all I got for today. So we're going to resume the rest of Unit 8 in tomorrow's lecture. And then we'll have a review session on Wednesday. We'll probably do a little Unit 9 because I don't want to have a 10-minute lecture. Like, why do class for 10 minutes at all? So, yep, that's all I got. Make sure that you Get quiz number 3 in. It is due tonight. Lab number 2 is due tomorrow. Try and get those things in because there will be another quiz coming up for Unit 7 and 8 that you'll probably want to try before you take the exam. And then the exam, of course, is going to be on Friday this week. So stay on top of stuff. Make sure you're asking me questions. Send me email. And I'll get to it as soon as I can. Have a wonderful rest of your evening, and I'll see you tomorrow.